This is your Orgo News team bringing you your 905 news with anchorwoman Katie Kellogg and reporter Kate Foley.
This is Katie Kellogg, and this is what's happening in your world today. Another episode of food poisoning by Saiga Dining Hall has struck the students again. Breaking news, this just in. Kurt Alder and Otto Diels have created the new DielsAlder reaction right here in our lab. We have Kate Foley there with them right now. Let's go check it out.
Hi, Kate Foley reporting live here with organic chemist Otto Diels and Kurt Alder. Yeah.
Our reaction involves the 4-2 addition of a diene and a dienophile, in which the HOMO on the diene reacts with the LUMO of the dienophile. In this particular example, the aldehyde group on the dienophile functions as an electron withdrawing group. The reaction involves the rearrangement of the pi electrons such that the pi electrons from this double bond swing down, forming a new sigma bond. Pi electrons from this double bond move up to form the new pi bond, and the pi electrons from this double bond swing up to form the other new sigma bond, thus resulting in the cyclohexane product.
So here for this specific reaction, we are illustrating the endo rule. So for the diene, we have an electron donating group, and the dienophile, we have an electron withdrawing group. So over here, we have the resonance to show how these inductive effects determine the cycloaddition. So here on the diene, we have this methoxy, which has a lone pair here that will donate down and move these bonds to produce a negative charge on this carbon and a positive charge on this oxygen. Over here, we have the dienophile with this ketone acting as the electron withdrawing group. So it's pulling the electrons towards this electronegative oxygen. And you end up with a positive charge on this carbon and a negative charge on this oxygen. So that resonance forms determines the partial charges and the inductive effects here. So this dienophile is going to end up with a partial positive charge there and then a partial negative charge on this diene. And that will determine the way in which the bonds move. So you get a bond moving here, bond moving there, and a bond moving there. And then this will determine the stereochemistry outcome of the product. And the endo rule is that those two substituents off the ring end up being cis.
Thanks for that, Kurt and Otto. I think I get it now. What about you, Katie?
Yes, I think I do, Kate. Let's see what other HWS students think.
How do you feel about the DielsAlder reaction?
Excuse me, how do you feel about the DielsAlder reaction?
Stop following me. Hi, Matt. How do you feel about the DielsAlder reaction?
Can't figure it out. Trying to make an 8-membered ring doesn't work.
Thanks for your question, Matt. So, looking at our past examples, you would probably think that this 6-membered diene and this 2-membered dienophile would work together to create this 8-membered ring. But wait, if you look over here at the MO analysis, which is an important part of the DielsAlder reaction, you would see that the molecular orbitals don't seem to match up. So the HOMO of the diene works together with the LUMO of the dienophile. So if you look at this plus or minus notation, you would say that this HOMO brings back over to this molecule. And you would have a plus, a node, a minus, a node, and a plus. And the LUMO of the dienophile would have a plus and a minus. So these work together great, while these do not. And that's why you would not be able to get that 8-membered ring.
Same thing.
Thanks, Kate. It makes so much more sense.
No problem, Matt. Back to you, Katie. Thanks, Kate, for that marvelous explanation. All right, folks, we got one last surprise for you. Kate Foley tracked down another beloved organic chemist to get his opinion on this new and revolutionary reaction.
Professor Pelkey, how do you feel about the DielsAlder reaction?
I think it's amazing.